Now let's move to forced vibration case and see one harmonic case which I just showed you, and see whether the peak response of this model against the same harmonic loading matches with what I have calculated analytically in my Excel sheet or not. So I review that again, that I selected this harmonic loading with this P naught and this omega bar, and then I actually calculated the analytical response, the steady state response, using this expression, and then I plotted it here. So this is my actual harmonic loading. This obviously I will be inputting in ETABS now, and the resulting response from my single degree of freedom system, the motion of that lump mass should be this one. So this should match with the analytical values. So let me now go to ETABS and open the same model which is not run already, so that I can show you how we can define a harmonic loading in our ETABS model. So the process of defining the harmonic loading will start from defining the harmonic function. The first step will be that we will be actually defining a function, the same function, harmonic function, and that function will be assigned to a pattern actually, and that pattern should include that point load which is applied to our lump mass. So let me first go for the rendered view, because that is easy to visualize. So this is my extruded view, and currently the joint labels are already shown, so let me uncheck that. So I will apply load here at this particular node, or I can also apply here. It will be same because the beam is rigid already, so I can apply in the middle or at any of these two ends, it will be same. But let me apply a force, horizontal force of harmonic nature, having a peak amplitude of you can say 1000 Newton, which is given, and having the same frequency as the given frequency of applied loading. So let me first define a harmonic function. So I'll go to define and functions and then time history. So here you can see that there are several types of functions which you can define. We will be using sine function and add new function. And here I have to provide the characteristics of that function which will be assigned to a particular loading, and then the analysis, dynamic analysis, can be performed. So I have already made one function, so let me just modify that. So this harmonic is already there, and I'll modify this already made function. Obviously we have to give some name to this function. This will be the time period of that function. This number should be same as what is given as the given loading. For example, let me go back and show you here that the time period of the applied harmonic loading was 0.897. So I have actually used the same number here. So this is the time period for that harmonic loading. Number of steps per cycle, I just use 50 because the program will be using the step-by-step direct integration, so it requires to discretize any given function to generate that table. So the applied loading is actually defined numerically. Number of cycles, I just give 10 cycles, so this will actually constitute 9 seconds of loading. And amplitude I set to 1. So the peak amplitude is 1. My plan is that I will apply 1000 Newton force as a point load on my lump mass, and then I'll multiply that 1000 loading with this function. So the peak amplitude of the resulting function will be 1000 Newton. So I just keep it peak amplitude as 1 here. So I click OK. So now my harmonic function is defined. Now the next step would be to make a pattern and in that load pattern I apply 1000 kilonewton point load, and then that pattern will be given with this function and make a load case. So I go to define and then load patterns, and here you can see that I have already defined a pattern by the name harmonic, and its type is other because it was not, related to any of the predefined load types, and self-weight multiplier will be 0, and I'll simply add that pattern. Now within that pattern I will apply 1000 Newton force at that particular node, which is this one. So I now select that node. Actually, in this particular case, the duration of the loading was already given. It was 10 seconds, right? So I just give 10 cycles because the time period was almost 1 second. So in order to reproduce that same duration of loading, I selected 10 cycles. But actually, it should depend on the actual loading scenario, right? For example, in case of harmonic loading, even if you know that the loading may remain for many minutes, at least you should run the analysis for that much amount time, in which the structure, if it wants to resonate, it can have that phenomena, and that model can capture that resonant phenomena. So the loading should not be very small, only maybe it should not be only few 3 4 cycles. It should be long enough to actually capture all dynamic effects in your computer model. So if your time period is like the structure's own time period is like 1 second, it should be at least more than 10 seconds or 15 seconds. So if the structure wants to build up some response due to a phenomena like resonance, it have that time to build that response, right? If you are interested in the steady state response, the loading should be significantly longer than the time period of the structure itself. Currently, in our case, the time period is 0.314 seconds. So it is less than the time period of applied loading, right? So therefore the dynamic amplification factor is not significantly higher than 1, and this is the reason that the response is looking very similar to the applied loading, which means the structure is in this particular case is showing a response which is very similar to static response. But this will depend on this omega bar which is given. Obviously, the characteristic of applied loading, the frequency of applied loading, is what is going to excite the dynamics of that structure itself. So in order to apply that point load at the lumped mass, I select this node and I go to define. Actually, I go to assign and then joint loads and then force. And here in this form, I will be actually providing 1000 Newton or 1 kilonewton force. For example, I type 1 here, 1 kilonewton, and I select the load pattern of harmonic which I just created, and then I click on maybe replace existing loads, and then you can see that 1 kilonewton load is applied here at that end. Now this load pattern by the name harmonic have 1 kilonewton load in it. When that pattern is multiplied by a function, that load will become dynamic in nature. So we will multiply this point load by the function which we have defined. So this will become our actual dynamic loading which we want to apply, and this we will be doing actually while defining the load case. So I go to now define and load case, here load cases, and by the way you can see here already two load cases are defined. So let me just click on one and modify it to show you how you will be actually doing it. So I give the name of the case first, then I have to select the type of that case, obviously this is the dynamic analysis, so it should be time history. And within time history, I have several options here. Two are linear and two are non-linear. I have linear modal and I have linear direct integration. So both of these options, any of these options actually can be used if your computer model is linear, which is our case in this case. But if our computer model is non-linear, we can opt from non-linear model, which is fast nonlinear analysis, FNA, and nonlinear direct integration. So we can, let's say, select the linear model in this case. And then here in this area, in this list, I have to list down all the load patterns with their functions which I want to apply in this time history load case. So for example, I can add one more, and you can see here that the second row is added. Previously I just added one. So first I select the load type. Either it should be a load pattern or it should be an acceleration pattern. Obviously for seismic analysis, for applying the actual ground shaking at the base, we will be selecting the acceleration pattern. But for this particular case where we are applying harmonic loading, we are selecting load pattern. Then in the load name, we will be selecting that pattern name which we have actually created. This is harmonic. And then the function which should be multiplied by that pattern. We have already defined a harmonic function. Actually, we name that also harmonic, so I'll select that. And the scale factor is a multiplier which is multiplied by the loading before the application. So we can just keep it 1. So we can have this row, obviously 1 is added, so I'll delete this one. We can have one row, this one, and this will ensure that my harmonic load pattern, which contains 1 point load, will be multiplied by a function which is also having the same name as harmonic, but we know that it is a sinusoidal function with a given frequency. And these will be multiplied and then applied as a dynamic load, right? At the same point where that pattern force is applied. Now, since we are using the linear modal analysis method in the time history, so I have to select from where the modal analysis results should come from. If I go for the direct integration, then it doesn't require actually the modal analysis results. So if I go, the form is changed now. If I change from linear modal to the linear direct integration, if I go back to again linear modal, you can see here that the option to select the modal case is there. So you can select the default modal case. Let me now select the, let's say, direct integration and explain that form. You have to select the number of output steps. When the dynamic analysis is run, how many steps you want to see as an output. Obviously that if you want to save the results at each step of applied loading, this number should match with the total number of steps of applied loading. So if you remember that I gave 50 steps in harmonic loading and I give 10 number of cycles. So 50 steps in one cycle multiplied by 10, it is total 500 steps. And for that particular time period which I gave, the time step was 0.018 second. You can confirm that also. I can click OK and go back again to define functions and time history, and I can modify that function, and then you can see that the delta t for this harmonic loading is 0.018. So all values of function are equally spaced at 0.018 second. So I simply go back and give the same delta t in my analysis load case because I want to see the results for each and every analysis step. If you want to reduce the analysis time, you can give a larger output time step size, but I give as same as the time step of the applied loading. Then damping, you can see here that you can define the xi value directly for your structure. This is the single degree of freedom system. So I'll be directly using the modal damping option, and in that if I go to modify show modal damping parameters, the program can ask me here that I can define constant damping for all modes, which is this number, and I can give 5%, let's say, which was given in my question also. So this is 5% damping given by default, so I can modify this number if I want. If I can click OK, OK, and then OK, the load case will be defined. So before actually going to the analysis, let me show you the second form also, which was linear modal. If I click on linear modal, I have to first select the modal load case. Obviously first I have to give the same pattern and same function, etc. Then time history motion type is periodic or transient. We mostly select transient. Number of output time steps same, and then output time step size same, and then finally modal damping. This method of analysis requires only modal damping, so you can give, let's say, 5% directly here, right? But the direct integration have the option for both modal damping as well as mass and stiffness proportional damping. But this linear modal response history analysis only has the modal damping option, because it only needs to define the damping for each mode separately, and the damping matrix is constructed at the end. So I'll click OK. I'll click on linear direct integration, and then finally I click OK. So this will define my harmonic load case. So this load case is now ready for running. But one more experiment which I can do is that I can define a truncated harmonic function. So let me cancel this and go to again define functions and then time history. And in the second function which I defined, I show you what I did, that I actually kept the same harmonic function, but I just added one last point. Here you can see the loading was up till 8.9 seconds and it becomes 0 at that particular time step. But I added another time step which is 15 seconds and the loading is still 0. By doing so, I will be actually carrying out the time history analysis up till 15 seconds. So I want to see the response of the structure after the loading becomes 0, and the effect of damping will be clearly visible in that free vibration response. So because in the first 9 seconds the structure will be under forced vibration response, so the effect of damping will not be visible, but it will be visible when the force will become 0 and the structure wants to sway under its own dynamics. In that case, you will see that ultimately the loading, the response will reduce and become 0. So let's also run the time history analysis for this kind of a truncated harmonic function. So I copied that same load case again, but this time the function is replaced by truncated harmonic function. So I go again to the same load cases, and in this harmonic truncated load case, you can see that everything is same except the function is now replaced by harmonic truncated. So everything is same. So and obviously the number of output steps will also be increased now, because now you want to run the analysis for 15 seconds and not for in 9 seconds, for example. So now let me run the analysis for harmonic case and harmonic truncated case also, and we will see the results, the forced vibration results at the end. So I have already run that analysis against these two loadings. So let me open that. So this model is run already. So let me show you first its board shapes maybe. This is the same model which I just showed earlier. So let me again just confirm that it is having the same time period 0.314 second. So dynamic analysis is run already. So let me again go to display deformed shape, or I can use this button also. And in that, now let me select the case, and in the case let me select harmonic. So now you can select the time, or a particular time, or absolute maximum or minimum, for example. So maybe I can go for maximum, for example, and I can click on apply. So this is going to show me the maximum deflection against this harmonic loading. So let me start animating it. So this will animate between the undeformed shape and the maximum of the deformed shape. So any of the response results, for example, the maximum, for example, the maximum shear or maximum moment can be seen against this kind of loading. So I can click on, for example, this display frame forces, and I can see, for example, the shear force, shear 2 against the harmonic loading, and let me select the maximum, for example. So this is going to show me the maximum shear values. Now I want to show you the displacement versus time history of this lumped mass or this beam, rigid beam. In order to plot that, let me first go for the undeformed shape using this option, and I actually need the node label of this node, or maybe this node, or maybe in the middle. Any of these node label is required to plot the displacement time history, because this is a rigid beam. So the displacement of node number 1, node number 5 and node number 2 will be same. So I can plot any of these, you can say 3 points, displacement of any of these 3 points. So let me show you how I actually get these labels. I click on this set display options, and in that object assignments I can click on labels here and then apply. So this will show me these numbers, which are node labels, joint labels. So now in order to plot the displacement time history, I'll go to display and then plot functions. It will give me a new window, and in this window I can plot any function from any analysis results. So let me just name this plot, give some name, and then select the load case, which is harmonic first. The horizontal function is time, and the vertical function I have to select. So if I click on this vertical function button here, I'll be seeing this form. I can add any vertical function by clicking here on this f of x, and this will show me a new form which can, using which I can have any function on y-axis actually. So let me add a new function, although there is already a function displayed and it is plotted already, but let me add the displacement of joint label 5, for example. So I can click on this button actually, and let me call it joint, select joint displacement. So the new function is here. I can give any name to that function here in the form below, and then it is joint displacement. Story number I have to select, it should be first story, and the joint label should be 5. So story 1 have 3 joints with these 3 labels, so I can select the middle joint maybe, although it will be same for all 3 joints displacement. And in which direction you want to calculate, you want to show displacement. Ux is the x direction, and response type obviously is displacement. It can be absolute displacement also, but currently it will be showing me the relative displacement. So using this way I can just click OK, and the new function on y-axis is available for me. If I can just add it here, it will be now plotted on y-axis. So I can remove this displacement named function and add this pf1, which is actually the displacement of node number 5. I can see that this orange line now is the displacement of joint number 5. Let me go back again to the same vertical functions form and add this displacement also. And if I can click on this button, I can see that the function name displacement, this one, is also the same displacement of joint story 1 joint 5. So let me change it to maybe joint 1, right? And pf1 will be my function for joint 5 at the same story. So the color will be red for joint 1 and orange will be for joint 5. If I click OK, and if I plot both of the functions on y-axis with respect to time on x-axis, I click OK, you will be seeing that both of the you can say numbers, they are overlapping actually. So if I only plot, for example, the function name displacement, if I just remove pf1, it will be this red line and the orange line is exactly on top of it, which means that the beam is exactly behaving in a rigid manner as we have anticipated. Now the displacement response is showing some higher value in first 2 cycles, but after that from the 3rd cycle onwards the displacement is almost constant with almost the same number as we are getting from the analytical results. If I go back to my Excel sheet, you can see that I am getting the peak displacement of around 0.7 second, 0.7 millimeter. So this peak number is what? 0.698, which means almost 0.7. And when I go to ETABS and go here in the steady state response case, the peak value is same as what I am getting, around 0.707. So almost same as what I am getting from the classical solution. But the mismatch will be there in the first 2 cycles. And you might guess the reason of this mismatch, that in my analytical solution, I have not considered the complementary part of the solution or homogeneous part of the solution. I assumed it to be the steady state response. So the response is not matching in first few cycles where the complementary part is also included in the solution. Obviously, the program uses step-by-step direct integration. It doesn't use the classical solution method, but it can capture the complete response, including the complementary and particular part of the solution. And finally, the response is stabilized to steady-state response, and it is exactly matching with what we are getting analytically. So not only the peak amplitude, you can see that the first, for example, 1 cycle and 2 cycles, the first 2.5 cycles are completed in first 2 seconds. So you can confirm from here also the first 2.5 cycles are completed in 2 seconds. So the amplitude and frequency of the response is matching with what we are getting from the numerical solution in ETABS. But the amplitude in first 2 cycles is not matching because we haven't added the complementary part of the solution, only considered the steady state response. Now let's plot the same function but for the truncated harmonic load case, where we have carried out the analysis for 15 seconds and the loading was discontinued I think around 9 seconds, and after that the structure started to vibrate in free vibration manner. So let me select a different load case here, and it is now harmonic truncated. And now you can see here that after 9 seconds, when the loading is removed, the structure now started vibrating in a free vibration manner, and the amplitude start decaying because of the effect of that 5% damping which we have provided. So by 15th second, the structure is almost having negligible displacement. So if you just zoom into that free vibration portion or free vibration part, you will be seeing that actually it is completing almost 3 cycles in 1 second. So if you start counting from around 9 second to 10 second, you will be seeing that it is completing almost 3 cycles. And it is due to the reason that the natural time period of the structure is 0.314 second. So which means that it will take 0.314 second in one cycle, in completing one cycle. So when it is allowed to vibrate freely, it is exactly following its natural frequency. But in the forced vibration case, in the earlier case here, you will see that it is following the frequency of the applied loading. So this is the difference between forced vibration uh, case and free vibration case. If you reduce the value of damping from 5% to maybe 2%, you will see that the rate of decay of this amplitude in the free vibration phase, that rate of decay will reduce. So it will not decay very fast like this. And if you increase like maybe 7% or 10% damping, then it will decay with even faster rate. So that's how you can apply any dynamic loading actually to your any computer model. Just think that now your single degree of freedom system is replaced by any real building, and your applied loading is also, it may not be always harmonic, it may be of any other nature. It can be impulse loading, it can be random dynamic loading, or it can be periodic loading, for example. So let me go back again to show you some other kinds of loadings. Let me open that same model again.